Hello and welcome to our What's New in WAVE and WAVE-RT presentation. My name is Evgeny Shapiro. I'm the Product Manager for Fluids at Realis Simulation, and in this presentation I'd like to take you through the new and exciting features of our 2024.2 release. WAVE and WAVE-RT provide high-fidelity modeling capability for internal combustion engine development. With WAVE Product Suite, our customers can accelerate virtual product development and leverage the latest innovation in R&D in 1D and real-time CFD space. Realis products deliver a personalized experience while minimizing the development costs and placing our customers firmly at the center of decision-making. So let us dive into the 2024.2 release content and discuss how these new features in 2024.2 can help you accelerate your CAE analysis workflows and create more accurate models. 2024.2 release is packed with features addressing simulation challenges our customers are facing. In this release, we have been heavily focusing on usability and support for workflow acceleration for 1D and real-time CFD analysis. In the new application and functionality category, we have new dedicated support for rotary engine modeling, simplifying setup of this type of the engines considerably. Workflow for modeling of controlled pressure drop flow paths is also simplified by the direct implementation of this functionality in WAVE. Control and calibration of 1D CFD models will also benefit from the new sensors, allowing users to sample data at a specified crank angle. Continuing with the improvement of the physics modeling, in this release we have a new heat transfer correlation for hydrogen combustion, which also can benefit other fuel types, and a new diesel predictive NOx model in WAVE, enabling accurate NOx emissions prediction for diesels and diesel-like fuels. In the user experience category, we have enhanced the usability of the case table through several modifications which improve navigation of large case tables with a large number of cases and a large number of parameters. The headline workflow enabling feature of this release is a new coupled optimization process with modeFRONTIER optimizer from ESTECO for WAVE, which we will cover in more details later. This feature is enabled by the new option to remesh automatically 3D components at the start of the simulation, applying the values of parameters which affect these components directly from the case table. The flap valve support in WaveBuild 3D also allows our acoustic users to directly embed flap valves in the complex silencer components. The new PID auto-calibration tool will simplify the process of controller calibration and analysis for both new and experienced WAVE users. Furthermore, we have added a new functionality allowing users to export parameters in user libraries, which allows users to create user libraries of controllers, parameterize them, and easily share them within the organization. A new and improved session comparison tool available in this release helps our users easily compare sessions and navigate to the sources of differences between them, which substantially improves the traceability of the changes between different builds of the models and also helps troubleshooting. Finally, we are now officially supporting all versions of DSpace, hardware-in-the-loop platforms, and A&D Helios platform. Let's dive deeper into a selection of these features. The rotary engine compact size and high power-to-weight ratio makes it a popular choice for UAVs and small aircraft, as well as sports cars. Recently, rotary engines have gained attention for use in hybrid configurations and as range extenders as well. Modeling of the rotary engine in our previous software releases used the reciprocating piston analogy, which represents each combustion volume of the Wankel engine as an equivalent reciprocating piston cylinder. This approach required users to calculate equivalent geometrical parameters of the reciprocating engine cylinders and also introduced a small discrepancy in heat transfer areas. In this release, we have introduced a dedicated Wankel volume element, allowing users to input parameters of the engine directly and simplifying the workflow. The heat transfer areas calculation is now matching the geometry exactly. An updated example of two-rotor 3.9-liter Wankel engine in our engine database in Wave installation shows the application of the new Wankel volume element and the input of the geometry parameters and thermal conditions. Let us have a look at our next feature, controlled pressure drop ducts. Reflecting correct pressure drop is very important in 1D CFD models as it directly affects engine performance, fuel efficiency, acoustic performance, and emissions. In some models, it can be useful to reduce the complexity of the model by replacing a complex component with a pressure loss specification in order to achieve faster runtimes. In this release, Wave offers such a functionality by enabling controlled pressure drop ducts where the pressure loss can be specified directly as a constant or as a profile as a function of mass flow rate or volume flow rate. Behind the scenes, there's an automated controller which will adjust the friction on the duct to match the target pressure drop. The controller is fully automated and it exposes one tuning parameter, controller aggressiveness or controller settling time. The default value is calibrated to be safe for most applications. However, the users can also adjust it if required. Let's have a look at our next feature, modeFRONTIER coupled optimization process. It is in fact a collection of features in Wave which enable a new node available in modeFRONTIER to ESTECO's customers on request. Automation can substantially improve efficiency in DCA and design workflows, and using automation algorithms to determine geometrical parameters which deliver the best possible performance for components such as mufflers and silencers, for example, can save engineering teams time. It can also deliver designs which are more optimized than would have been otherwise possible with manual approach or design of experiment studies. Wave capabilities in model parameterization and its accurate acoustic solver, combined with modeFRONTIER optimization capabilities, offer a great workflow which can increase efficiency in acoustic design projects. The new node, which is available in modeFRONTIER to ESTECO customers on request, allows users to query parameters in Wave models and directly drive Wave solver, varying model parameters to achieve target results. Any simulation output, direct or derived, which can be plotted in our post-processor RPost, can be set up as an optimization target in modeFRONTIER, providing excellent flexibility of the workflow setup. So what does the optimization workflow look like? The workflow starts with parameterization. So for example, we can parameterize a muffler component in WaveBuild3D, setting up diameters of the internal pipes, perforation parameters, canister geometry as parameters which are available in Wave simulation. We then set up the simulation itself, the data acquisition and the acoustic solver in a way as would be appropriate for a baseline simulation with the baseline geometry. We then set up the post-processing session, plotting the parameters which we would like to optimize, such as, for example, back pressure or overall sound levels. This Wave session and our post session can be now loaded directly in modeFRONTIER, queried for the parameters which Wave solver Wave session exposes, and an optimization process can be set up driving these parameters to match the targets defined in their post session. For example, in this case study, which is available to customers of ESTECO and customers of Realis Simulation, we are showcasing constrained design study aiming to identify a muffler design with lowest possible back pressure and the best match with the target SPL prescribed by the designer. The parameters of the muffler include the internal pipe diameter, external canister diameter, the number of holes in the perforation, and the muffler length. And the constrained design study performed in modeFRONTIER starts with a baseline muffler with parameters for back pressure and overall sound level shown in the red on the plots to the right, and ends up with a constrained best design with back pressure substantially lower than the baseline and below the target of 1 bar, and the sound pressure levels closely matching designer prescribed target curve. This simple example takes approximately 1 hour to achieve the best design on a standard 8-core workstation using parallel capabilities of WAVE and modeFRONTIER to iterate through 500 design points. The same workflow can also be applied to other optimization targets, so it's not limited to acoustic optimization. It can be used for model optimization, heat transfer optimization, and so on. In a simple statement, if it can be parametrized, it can be optimized. Continuing with the theme of simplifying manual workflows, our next feature addresses the challenge of simplification of controller development in WAVE. In the absence of any obvious starting point, such as for example a previous similar model, choosing gains for a PID controller can be challenging and can involve a manual iteration process. This is time-consuming, so in this release we introduce a new workflow in WAVE aiming at automating this process. If we look at the process of the controller development, it follows certain stages. So there's a static analysis stage where we're analyzing system response to a sweep of controlled input values. There's a dynamic analysis where we're analyzing the reaction of the system to a step change in the actuated quantity. And then there is a calculation of optimal gains, typically done based on the results of the dynamic analysis. Finally, there's a validation process where the gains are applied back to the system and the system is exercised through a larger set of operating points. All these stages are automated through the new PID tuning task available in the RDesk Wave plugin and are illustrated in an updated PID calibration tutorial which walks the user through the development of the throttle controller. The simulations which are necessary for the static analysis and dynamic analysis of the system are performed in the background by automatically creating required wave sessions. The PID tuning task also benefits from distributed option, so it can be used in conjunction with RDM to substantially accelerate the wave simulations required for static and dynamic analysis of the system. Our new session comparison tool, available in 2024.2 release, addresses the challenge of reducing the time spent on model builds comparison and troubleshooting. Troubleshooting models is one of the most time-consuming processes in 1D CFD model development, and it frequently requires tracking changes from multiple model builds, and the ability to compare models quickly and efficiently is a substantial time saver. In previous versions, in WAVE, we introduced a session comparison tool that generated a table of differences between the two sessions. Such a representation is useful for small changes, but the volume of output information for complex changes could make the analysis difficult. So in this release, we are delighted to introduce a new session comparison tool with enhanced comparing and filtering capabilities. It makes it easy not only to find and analyze differences between sessions, but also allows users to navigate directly to the source of those differences in the model. Additionally, results can now be saved in an easy-to-use CSV format for future reference. The functionality is accessible through the same toolbar button as the previous version of the comparison report. It is also available not only to WAVE users, but to users of other Realis products plugins within their desk environment, for example, to Ignite, Vectis, and Fierce Falcon users. For example, here we have a number of builds of a motorcycle model with incremental changes between the builds, and we can use the comparison tool, which is located on the toolbar here, to pick a session to compare against the session currently open, build 03, let's say build 03A. We can see the comparison results between the sessions presented in the same form as the session tree in the model, with all the changes introduced between these builds, allowing us to easily track the changes and also navigate to the items in the model where the changes are introduced and revert them if necessary. This functionality allows us to track changes very easily, and we are using it extensively on our engine model building projects at Realis Simulation. In addition to the main highlights, this release introduces a number of new features, usability and productivity enhancements. The first group focuses on improving heat transfer and knock modeling. The option to apply Washington gas exchange heat transfer coefficient helps users switching to WAVE from other tools. In these circumstances, it's sometimes important to maintain a one-to-one mapping of heat transfer coefficients, and to streamline this process, WAVE and WAVE-RT now offer the option to apply the Washington heat transfer coefficient with valves open, not only when intake valves open, which is the conventional approach in WAVE, but also when the exhaust valves open, which is the approach taken by competitor stalls. The knock intensity can now be interpolated to knock integral of 1 when knock occurs. This small enhancement improves the accuracy of knock intensity reporting, particularly when using larger time steps. It also aligns WAVE implementation with that of WAVE-RT. For knock control purposes, it's sometimes preferable to use the knock integral, which is a smooth, continuously varying quantity, instead of knock intensity. This is made possible by the new knock integral sensor, which we have introduced in 2024.2. WAVE-RT in this release benefits from a number of enhancements. It's now possible to specify the simulation start angle by parameter, which is useful for hardware envelope and software envelope implementations of stop-start scenarios. Users can now actuate orifice areas directly. In previous releases, area actuators were converted to diameter actuators. We have also added a new limiting capacity RT sensor, which provides information about the stability limits of the system on the fly during simulations, helping users analyze hotspots and prevent divergence. There's a number of changes in WAVE tools and infrastructure. There's a new flame speed generation GUI tool with parallel capability, which makes it possible to generate flame speeds for user-defined fuels through a user-friendly GUI, and also run flame speed generation in parallel on HPC architectures, which can substantially accelerate table generation process for complex fuels. Our desk features upgrade of Qt framework, which brings in support for display scaling on Windows, as well as uniform look and feel between Linux and Windows platforms. Finally, there's a number of improvements in the GT Power model importer, targeting users who extensively use submodels in GT Power, which makes it easier for them to switch to WAVE. Finally, let us have a brief look back at the key features in the previous release, which may be of interest to our customers. In 2024.1, we have added predictive combustion for biodiesel applications, support for complex mapped injectors, and real-time modeling for rotary engines. The navigation of WAVE Canvas has been enhanced to help users easily locate elements on complex canvas with find and zoom to functions, and WAVE Build 3D meshing has been improved to allow precise mesh alignment and actuated orifice support. Thanks for watching our new features presentation. I hope you enjoyed it. If you have any questions about these new features or would like to explore how Realis simulation products can help you optimize your CE workflows further, please don't hesitate to reach out to us at support@realis-simulation.com.